Hello everybody. So in the last class we were discussing about the DC generator, mainly about the structure of the generator, the way the commutator poles are segmented, the way the brushes are positioned in the neutral zone, so as to get an output that is ripple free, that is containing as little ripple as possible. Today we continue the discussion on the DC generator and complete the equation for the generated EMF across the brushes. We saw in the last class that the generated EMF across the brushes, e.g., is given by N phi Z by 60. This is the volts, and we also did a small example to consolidate this understanding of this particular equation. Now here N is the RPM of the rotor, the armature, phi is the flux per pole, Z is the total number of conductors in the armature. Here we have always been assuming that there is just one set of north and south poles, and in between you have the armature, and inside we also draw the segmented commutator. So we have the commutator which is doing the job of rectification, and of course the brushes placed in the neutral zone. So for such a configuration, so you could have n slots. So if there are n slots on the armature, there will be n coils, and if there are n coils, there will be n segments on the commutator. Now we could have multiple pole pairs. We see that here you have one pole pair, one north-south pole pair. Let us say we place the pole pairs north, south, north, south, north, south. Alternately, poles are placed of opposite polarity, but the pole pairs are diametrically opposite, meaning this is one set of pole pair, this is another set of pole pair, and we have another set of pole pair here. So you have three pole pairs arranged in this fashion. So these pole pairs and of course here you are going to have the commutator with the segments and the brushes placed appropriately in the neutral zone. You see the neutral zones will be always in between, at the midpoint in between two poles of opposite polarity. So it is always, that is where you will get zero voltage induced onto the coils, and therefore the brushes have to be placed in the neutral zone. Now here you have three pole pairs, and therefore to incorporate also the finite number of pole pairs, which need not be always one, the modified equation for the generated EMF, e.g., is pole pairs P. P is the number of pole pairs N, phi, Z. All others mean the same quantities as we had described earlier. So, P will be the number of pole pairs. As poles do not exist independently, they always exist in pairs. You can't have a pure north pole or a pure south pole. We normally talk in terms of pole pairs, or if you want to talk in terms of poles, they will always be even numbers, multiples of 2. So, number of pole pairs, N is the speed of rotation in RPM, phi is the flux in Webers per pole. Per pole means per pole pair, and Z is the total number of conductors in the armature. So, Z is the total number of conductors in the armature. So, this would give you the induced EMF of a DC machine, a DC generator, which has P number of pole pairs, N is the speed of the rotation, phi is the flux per pole, and Z is the total number of conductors in the armature. Now, there is one important aspect that we need to study. We have the energy coming from the mechanical domain, goes into the magnetic domain, and then finally comes out through the electrical domain by means of the brushes, and this comes out as the induced voltage E g. So, one is applying a torque here. Now, if one loads here, that loading effect on the electrical side should percolate back and get reflected on the mechanical side, so that you draw more energy. So, there should be any load here should reflect as a reverse torque here, such that the prime mover, whatever is moving the mechanical shaft, should now apply that extra torque to overcome that load and still rotate it at the same RPM, so that you get the same induced EMF E g. So, this loading effect here in effect has made the prime mover, whichever is driving this shaft, to now give more energy to the mechanical shaft to supply the energy to the load. So, this is how in any energy conversion process, there should always be a loading effect which should percolate back. How does this happen? How does this loading effect back onto the shaft happen in a DC machine? Because that is an important thing to understand, and that is happening by means of what is called the Lorentz force. So, we saw that in the DC machine there are two important equations that you need to remember. One is the Faraday's law of electromagnetics, the alternative equation, which is E is equal to B L V. The other is the Lorentz force acting on the conductor. So, what is it? So, let us take a north pole and a south pole. And let there be flux lines. So, these are flux lines or B, which is equal to phi by A. Now here let us place a conductor and let a current flow through the conductor, and we are passing the current through the conductor, and that is going into the board. The direction of the current is going which is now we saw that when there is a current flowing through the conductor, by the right hand rule there is going to be a magnetic field set up around the conductor. So that magnetic field is, as it is going in by the right hand rule, if it goes in, then the fingers will encircle in a clockwise direction. That is, it is going into the board, the fingers are encircling in a clockwise direction. So which means the field will be in a clockwise fashion. So we have the field due to the current I, and that is in clockwise direction. So now you see what's happening. The field produced due to the current, the orange ones which are shown, and the field of the permanent magnet, they both are going to, the field is aiding, the field produced by the current in the conductor is aiding the north-south field, and below the conductor, the field produced by the conductor, current flowing in the conductor, is against the magnetic field of the north-south conductor. So here it is against, and here it is aiding. So equivalently, we will land up with field distribution. So there is a current I flowing here, and because of the I flowing we had those things. Now the field on the bottom side of the conductor, it tries to cancel. So the field is weak and the field is strong on the top of the conductor. Whereas it is weak on this side. So this field is acting now like a rubber band which is trying to push the conductor down. So there is a force which pushes down because of the current I which is flowing through the conductor I. Now this force is called the Lorentz force. Now there is an interesting rule to a memory tip for you to remember the direction of the force. If the thumb is pointing, take again the right hand, always the right hand. If the thumb is pointing in the direction of the current flow in the conductor, and the forefinger or the index finger is pointing in the direction of the north-south magnetic field, then the middle finger, which is at right angles to both the thumb and the forefinger, you see that all three fingers form the three coordinates of a system, and each is orthogonal to the other. So the middle finger now points in the direction of the force. So if you point the thumb in the direction of the current and the forefinger extended, which is now orthogonal to the thumb, pointing in the direction of the applied field, which is the north-south magnetic field, then the middle finger, which is also orthogonal to the other two fingers, will now point in the direction of the force, in the direction of the Lorentz force, and that is the direction in which the conductor will tend to move. So, what is the value of this Lorentz force? The Lorentz force F is given by a very simple equation, B into I into L, where B is the flux density of the magnetic field, and in this case it is the flux density of the north-south magnetic field that is being applied, and which is this. And then I is the current flowing through the conductor. Which in this case is this, the current flowing through the conductor, and L is the length of the conductor, So, this gives the force newtons on a conductor which is placed in a magnetic field B of length L, carrying a current I through it. So, the direction of the force, as I said, you use the right hand rule to find out the direction of the force. So, now let us apply this Lorentz force principle to the DC machine. So, we have the DC machine with a north pole and a south pole as shown here. Now, let us have the armature or the rotor, as one may call, circular fashion like this. Now, there are coils, and we will represent the coils in terms of circular conductors here, in this fashion. So on, like that. So, at a given instant of time, now this is the neutral zone, this is the neutral zone. There is no voltage being induced on this conductor and this conductor, so there is no current flow. Now, let us say there is a current flow in this conductor, and let us say it is going into the board, and because it is away from the neutral zone, there is going to be a current flowing in here. All these will be in the same direction with magnitudes varying. The one which is nearest to the south pole will have the largest magnitude. So, again this conductor is going to have zero current because it is in the neutral zone, and then here the direction will be opposite, coming out of the board with varying magnitudes. The one nearest the north pole is going to be having the largest magnitude of the induced current. Now, these are the armature conductors. Now, these armature conductors are connected to the commutators, isn't it? So, the armature conductors are connected to the commutators, and through the brushes through the brushes, we see that the external circuit is connected. Now, we apply a load to the external circuit which has a voltage induced E g due to the generator action, and there is a current that flows through the external load. Okay. So, this is a current I and there is a load R L. Now, this I is going to flow through the respective conductors, that is through the armature. Now, if we take a particular, conductor, let us say this particular conductor which I am showing here with the cursor, now that is flowing into the board. Now, there is a magnetic field which is being applied in this direction, and therefore, there has to be a force which is in this direction. You have the force. Likewise, this conductor will have a force in this direction. This conductor will have a force in this direction. All these forces will add up. Each conductor will apply a force in this direction, downwards. Okay. Now, the current is going, the current is coming out, and by again applying the right hand rule, you will see that the force will be applied, it will be in direction pointing up, and therefore, they all will be aiding. The forces on each current will be aiding. So, these are the forces, the Lorentz force due to the load current which is flowing through the armature. Now, this force is applying a torque on the shaft, and the prime mover has to overcome this shaft, which means now the rotation is in this direction anti-clockwise. This is the rotation of armature, but the loading effect is giving a rotating torque which is in the clockwise direction. So, an extra power has to be generated by the primary, which will try to force against this clockwise loading effect torque, such that the armature continues to rotate in the speed. So, thereby it draws more energy from the prime mover and dumps it to the electrical side. This is the energy conversion process on loading. Okay. So, this is how any load gets reflected onto the mechanical shaft and thereby acts as a load on the prime mover. So, having looked at the loading effect, we have one more important effect which we need to consider, and that is the armature reaction. Armature reaction is another undesirable effect that we want to avoid. You see that till now the in the consideration of in the discussion of the operational principle of the DC generator, there was a flux between the north-south poles and there was a coil, and due to the motion of the coil there was a current induced in the conductors of the coil and which flowed through the brushes and to the external circuit. But moment there is a current in the conductors of the coil, there will be a field around it. Now, that field is going to react with the main field of the north-south magnetic poles which has been applied. Now this will distort the way the field will look like, and the neutral zones which we thought were zero field zones where no induced voltage in the coil can exist, all these concepts are going to be a bit distorted because of the presence of the current which flows through the armature conductors. Now let us look at this effect, what it does. We have the north pole and we have the south pole. Still we are sticking with the same one pole pair, and let us have the circular armature. Now in the circular armature we are having the conductors. So let us have the conductors in the circular. And this orthogonal plane was supposed to be our neutral zone, where there was not supposed to be any induced voltage and thereby no induced current, because at this point the flux is equal to 0 in that direction. Now there is a flux, north-south flux, which flows in this direction. This is a flux due to the applied north-south poles. Now we see that there is current, and like in the previous loading effect diagram, let us say the load current flows through these, and in these conductors the currents are coming out of the board. Of course, imagine that there is a commutator here, the coils are connected to the commutator, brush is there, and the brush is connected to the external circuit, and external load current is flowing, which is causing the currents to flow through the armature coils. All these are happening. Now if we look at the flux distribution of these, now let me use a different color. So let us say there is a flux distribution in this, which goes like that. There is the fluxes which goes like this. So it goes this, you have the loops because there are currents flowing within these loops, and the direction again given by the right hand rule, we will be having something like this, clockwise. So this is the way the currents here. Likewise on this side also we are going to have a flux distribution or the field distribution. So let us say we have the field lines like that. Now this is coming out of the ring, and then by the right hand rule we could say that these are going to have anti-clockwise direction like this as shown. So you see at the center, these two are not going to contribute anything to the field. Now if you see at the center, at the inside the armature of the machine, the flux is flowing in this direction. The flux is flowing in this direction. You see all the fluxes are pointing up. So which means there is an effective flux which is pointing up in this fashion. So this leads to the following equivalent representation. So you have the north, you have the south, and I have the armature here, the circular armature, and what was supposed to be the neutral zone where no flux was supposed to be there. So we have one set of flux here. Now, this is the flux which is due to the north south pole. Now, there is another flux in this direction, because all these add up, okay, inside in the core. That is going to produce a equivalent flux in this direction, and this is due to the armature currents called the load current. So, armature current or the load current dependent on the load. So, you have these two fluxes, and we thought that in the neutral zone there was not supposed to be any flux, and therefore, any coil here will not have an induced voltage. But due to the armature current which produces these fluxes, that is, which produces the these loops here, which produces these loops here due to the currents flowing in the various conductors, has a resultant pointing like. Now, these two are going to have a resultant somewhere, let us say, along this line. So, this would be the resultant flux direction. Resultant flux direction. So, because of this, one major problem is that the brushes which were supposed to be located in the neutral zone, because in the neutral zone there is no voltage induced in the coil, there is no, at that point the brushes short circuit the coil and there is no problem. There is no huge circulating current. But now with the armature currents causing these flux, and this flux is always going to be in this direction, whatever may be the position of, will result in a voltage being induced in the coil. And that voltage which is getting induced in the coil due to this armature flux, armature current produced flux, will short circuit the coil and produce a huge short circuiting circulating current, and therefore I square R losses. And as a result, when the brushes are passing over that coil, there is a current flowing through that, and then there is an inductive reactance in the coil, because the coil is inductive in nature. It is trying to suddenly break the coil and there huge spark results. So, the sparking will also be very high in the brushes, and the brushes will go bad much more quickly. So, therefore, to avoid these two problems, one is the I square R loss due to the circulating current, and the circulating current itself will heat up the winding, and the other one is the huge sparking. We need to place the brushes in the neutral zone. So, we said that the neutral zone is always orthogonal to the main flux. Now, here we have the resultant flux, and therefore, orthogonal to that would be this, and this would be the neutral zone. So, the neutral zone has shifted. So, if this is the direction of rotation, so the neutral zone has shifted in the direction of rotation, it has gone a bit further, and therefore, the brushes will have to be placed here. Let us say we place the brushes here. Let us have the commutator. So, the brushes will need to be placed at this point to avoid the circulating currents, and also of course the increased sparking. Now, if it was so, if we just had to shift the like this, the problem would have been simple, but it is not as simple, the load current is a varying quantity, which means the red flux, the red lined flux which we are indicating here, which is orthogonal to the north south flux, the amplitude keeps varying. So, if this amplitude keeps varying, then the resultant could be in any direction depending upon the amount of load current. So, orthogonal to that only will be the neutral zone. So, we see that the neutral zone has a much higher band of angle in which it can exist at various load currents, and therefore, the brushes cannot be dynamically positioned as the load current changes. So, therefore, this flux which is created due to the load current or the armature current flowing in it is going to cause a problem. And this armature flux which is created due to the armature current flowing in the conductors is called armature reaction. Is called armature reaction, which is basically this flux. So, one could think of a solution Now, let me also put in the conductors, and this was supposed to be our neutral zone. We shall put in the conductors. There is one conductor representative value there. Let us put a representative value here. Machine. Then let us have the commutator. So, the commutator is also in place. So, this is the commutator, and we also have the brushes in the neutral zone. Now, what we try to do is have two small poles here. So, if we have these two small poles here and the brushes, and from the brushes let us wind it over the poles like that. Let us wind it over the poles. Okay, so, this is the negative, and from this brush also we will take it and wind it over the poles as shown here. This is plus. So, there will be a current which flows. Let us say this is the plus side and the minus side. So, we will have a current which flows like that in the external load. So, the current flows in the external load like that. So, it flows in through here, comes in this direction, goes like that, comes in here, then through the armature, through the armature like what we had drawn before. All these conductors here on this side of the pole, south pole, will be having through the board, and then here it is coming out of the board. So, this means into the board, and on this side the dot means coming out of the board, and you have currents flowing like that. Now, if you look at the nature of the winding here, we have the coil wound here and the currents flowing this, and by the right hand rule, applying the right hand rule, we will have a MMF, an equivalent flux. We will call this one as flux C, phi C, which is going in this direction. Likewise, here, due to the way the current is flowing here, we will have a phi C which is flowing here in this direction. Now, the armature reaction, that is the currents through the armature, that was producing a flux, in this opposite direction, which is in this direction. So, this is the flux due to the armature reaction. And then of course, there is going to be the flux phi due to the north south pole. So, you see there are three fluxes, the flux phi due to the north south pole, which is standard, which is what we want, and then there is a flux in red line which is orthogonal to the north south magnetic flux, and that is due to the armature reaction, as we saw the previous discussion. And then there is a third flux due to these poles which we have, small poles that we have added, and we have passed the armature, the load current carrying armature current through those small poles, such that there is a phi C which is in a direction which opposes the armature reaction. See that the phi C flux opposes the armature reaction flux. So, if the number of turns here on these poles are so matched such that phi C cancels out the flux due to the armature reaction flux, then the only flux that would exist is the north south pole flux, and this would still be the orthogonal plane would still be the neutral zone. Now, these cancelling poles, the poles that cancel the armature flux due to the armature current, the armature reaction, is called the commutating poles. They are called the commutating poles. This makes the flux due to the armature current, or in fact the armature reaction, 0, thereby still maintaining the same neutral zone positions, and thereby we need not shift the position of the brushes, and the brushes can still stay in the same position, and the voltages induced in the coils at the neutral zones will still be 0, and therefore no short circuiting currents, and therefore also no sparking, extra sparking or arcing when the commutator segments are passing over the brushes at that point, that is the neutral zones. So, this is an important concept, that is the armature reaction, which will be there in any DC machine, and that has to be taken care by using the commutating poles. So, the next topic that we will deal with is the excitations. So, there are different methods in which one can excite the machines. Now, what does one mean by excitation? We saw in the motor has the north pole, the south pole, these two is a pair, create a flux phi. Now, the flux phi called the field, that field is called, how the field is brought about is called the excitation. The current that brings about the field is called the excitation current, and the field or the field flux itself is called the excitation. So, how do we bring about, or how do we bring about the amplitude of the particular flux in the DC machine, and what are the methods in bringing about such a flux? So, that is called the excitation. So, the question that one can ask is, how does one excite the machine? And when they say how does one excite the machine, it means how does one set up the flux or the field within the machine, the base field, the north south field that we have been talking about till now. We have to set up that flux, that is called the excitation. So, any means or any current that is used for setting up the flux is called the excitation current, and any means or any circuit that is used for setting up the excitation field is called the exciter or the excitation circuit. So, excitation in short means that setting up the base flux inside the machine. Now, there are different various ways in which one can set up this flux within the machine, the field within the machine, and here are some of the methods which I am going to list down. One is we could use permanent magnets. Permanent magnets, that is the north south poles that we were talking could just be plain permanent magnets. Second is separate excitation. Then such a machine is called separately excited machine. Okay, such a machine is called separately excited machine. Or we could have shunt excitation. This machine is also called self excited machine. And then we have few forms of compound excitation. So, these are some of the methods that are used to set up the field within the machine. We shall see these methods, we shall discuss these methods and what its implications are in the operation of the DC generator in a short while. But this first method, that is the use of permanent magnet, then it is called the permanent magnet DC generator, wherein the north south poles are permanent magnets. See, the permanent magnets could be samarium, cobalt or rare earth magnetic materials. Alternate to using the permanent magnets would be to use electromagnets which generate the field equivalent to the north south pole pair. So, what is done is that you have a machine here, with a north south pole pair, which is the permanent magnets, and we have the armature and then we have the commutator, and on the commutator we have the brushes. So, let us simplify the representation here by assuming that there exists the armature. Okay. So, we just have the commutator here and the brushes attached, okay, which is going to generate Eg, and from the brushes we are picking up the voltage to be applied to the external circuit. Now, these north south poles are generated from, let us say, a separate voltage source, let us say a battery. So, we have a battery here, and that is wound onto the core like that, then goes in here, this is wound onto the next core and then brought down, connected across the battery. So, this battery here is supplying a current IF, which we call the field current IF. Now, the field current IF is flowing through, this is plus and minus, this is flowing through in this direction, goes in this direction here, flows through in this direction, okay, which sets up the field. And this field, so now no longer we have this north south, now it has become an electromagnet. Now it has become an electromagnet with the directions being set by the way the current is flowing through in this green wire as indicated. So, if we see the direction of the flux here by the right hand rule, we see that the flux here is in this direction. So, if the flux is in this direction, the direction of rotation is in this direction, because for the flux shown in this direction, we were showing direction of rotation in the opposite direction. So, this is going to generate a voltage Eg here. Now, the flux is being set up by a source, separate source here. Therefore, we say the excitation is separate. So, this is called separately excited machine. This is separately excited machine. This is a separately excited machine as seen here. So, now instead of taking the excitation from a separate source, let us take it from the generator output itself. That is, instead of taking it from this, we connect this to the generator output itself, which means Eg is applied to this. Of course, we do not directly apply Eg, so we have to put a series resistance. So, So, we put a series resistance to limit the current to whatever the required value. So, this is making a current IF to flow through it, flows through in this same path and comes back through here. So, this is the field resistance RF. Now, such a connection is called shunt connection or shunt excitation. Shunt excitation. Now, in this shunt excited machine, the field current is taken directly from the induced EMF of the motor. So, which means that the induced EMF, if it changes due to the loading effect, the voltage that is seen by the field coil will also change, and therefore, IF will change, and therefore, the flux or the field in the machine will change, and thereby changing the induced EMF further. So, therefore, the regulation will not be as good as in the case of separately excited machine. In the case of the separately excited machine, the field is constant, whereas in the case of the shunt excited machine, the field can vary, because the voltage which is generated also varies with the load due to the loading effect. So, we saw that one can connect in these fashions, that is either separately or taking it directly from the generator. One could also make combinations of these. We will see how we go about making such changes to get certain benefits out of the disadvantages which are existing in the shunt excitation. The compound excitation is consists of a shunt excitation plus a series excitation, which will try to compensate for the variations in the induced EMF. So, in the compound excitation itself, there are two varieties: the plain compound, and there is the over compound, and then there is the differential compound, which we will discuss in the next class. So, in the next session, we shall also try to get a feel for the voltage regulation, that is the voltage versus the field current curves, so that which will give us a better understanding of the various excitation, the advantages of the various excitations. Thank you for now.